Welcome back. Today we're going to talk about order reduction models for statistical physics and how we can solve those without doing statistical physics but purely from data. And the model that we're going to solve today is the Ising model, and we're going to do so by using the principal component analysis. So yeah, let's dive in. First, we're going to start with the physics. The Ising model is a model to describe the behavior of magnetic materials, and it consists of a lattice of spins that can be either up or down, and the interaction between these spins is described by this Hamiltonian, where we have in the first term the interaction between neighboring or between spins, and in the second term the interaction with an external field H. For our purposes, we're going to only handle nearest neighbors interactions, but for more general applications, we don't have to only use nearest neighbors interactions, but can let the spins interact from arbitrary lattice sites. Okay. Yeah, we can solve this system analytically with the Onsager solution. Yeah, it has the partition function, and the important thing for us is it has a magnetization that's just the mean of all lattice sites, and the magnetization can be computed analytically, so we have something to compare against. Okay, what we are going to do to discover the order parameter, the magnetization from data, we first have to generate data, and I did so from a Metropolis algorithm, and let's have a look at it. So here in this data set we have 75,000 configurations from our lattice site, and we can have a look at what's actually contained in there. We have the actual configuration, that's just the lattice. It's 28 by 28, and I have the corresponding magnetization, that's just the mean, and the temperature at which I simulated for this particular lattice. That, yeah, beta j is the inverse temperature times the coupling constant, and that's just a handy way to get rid of any temperature terms. Okay, so let's have a look at an arbitrary configuration, and there you can see in this purple area the spins are at -1, in the yellow area they are +1, and for different numbers we have different configurations. Okay, now that we know what data we have, we're going to talk about how we're trying to discover the order parameter of the system. And how we're going to do that is we're going to use PCA. PCA is principal component analysis, is a method to transform our coordinate system from this grid coordinate system into another coordinate system via this diagonalization of the covariance matrix, so that our axes point into the direction of the highest variance. Okay, so what did that actually mean? So if you have this image here, we have many data points, and we want to find, since our data is two-dimensional, we want to find the both directions in which the variance is largest. So the first one is obviously from bottom left to upper right, where we have our first principal component. And then, since this is a unitary diagonalization, we have to find another orthogonal basis direction to change our basis from this normal Cartesian basis into the basis in which along the axes the variance is maximal. Okay, how does that look for our Ising model? In our Ising model, we have a 28 by 28 matrix, so our vector space has dimension 28 by 28. And the basis vector looks like, for each of these pixels, they are an individual vector. So the pixel up here has 1 and then 28 by 28 minus 1 zeros. So yeah, we are going to find a transformation into another basis that the first new basis vector is along the direction of the most variance in this system, and hopefully that will correspond to the order parameter. Okay, so how are we going to do that? Since we have 75,000 configurations and that takes a long time, I'm choosing 20,000 configurations by random. And yeah, what we have here is just an array of these indices at which I want to use for my PCA. Then what we're doing here is we're going to store these into an array that we need for the PCA, and we're going to store the temperatures at which these configurations were simulated to have some corresponding or correspondence of where are the hot values in this new basis and where are the cold configurations in this new basis. Okay, so again, what we have here is a large array. It has 20,000 configurations, and each configuration has 784 entries. And in this temperature array, we have just for every configuration the corresponding temperature, and you can see it's again 20,000. Okay, so now we actually do the PCA, and that's super easy. That's from PCA, from sklearn, and yeah, it's just these 2 lines. Takes about 2 seconds, 3 seconds, and it's done. And yeah, we can visualize now how that actually looks like. Okay, what we see here is we plotted the first 2 components of our data. So P1 is the value along the first basis direction, and P2 is the value along the second basis direction. And you can see there's a lot of spread into this P1 direction. And we see two poles here where there are a lot of blue dots, and in the middle there are a lot of red dots. And also you can see in the second direction we have a lot of variance in the middle of the plot, and the sides there's almost none. Yeah, if you have a look at the color bar on these 2 poles, we have mostly cold configurations, and in the middle we have the hot configurations, which, if you think about it, makes total sense. Of course, for the Ising model, we expect that for cold temperatures we're in the ordered phase, so either all spins up or all spins down. That's corresponding to these both poles, so that might be all spins up and that might be all spins down. And in or other way around, since it's symmetrical, it's a symmetrical system, that doesn't really matter. And here in the middle we have the hot configurations where all spins are independent from each other and act randomly. Okay, if we then think about our basis transformation, we have the matrix lambda. That's diagonal, and on the diagonal are the eigenvalues, and they're sorted by the explained variance. So the first eigenvalue is the largest and explains the most variance, and then we kind of go into the following ones to explain less and less and less variance. So we can have a look at how many or how important the first principal component is compared to the following ones. And what we see is there is one principal component that explains a lot of variance, and it's an order of magnitude bigger than all the following ones. And you see that probably is the magnetization. The numbers down here is the number of the eigenvalue. So yeah, we have 28 by 28, so 784 eigenvalues, what you're seeing here, and here you're seeing the relative value of the explained variance. So all these should add up to 1, because we need to explain 100% of the variance, since in our original data we had 100%, so now we can't lose variance, but this one is clearly dominating. So now let's actually have a look at the difference between the principal component that we found without giving it any physical intuition and the order parameter that we actually know from statistical physics that it describes the system best. And let's look at the deviations. Okay, what you see here is on the left you have the magnetization over temperature. So here for low temperatures we have high magnetization, so we're in the ordered phase. For low temperatures we have almost no magnetization, so we're in the chaotic phase. And for this dashed line is the analytical critical temperature that we know from the Onsager solution. And on the right hand side you have the same plot, so now it's not the magnetization but the first principal component over temperature. Yeah, you can see it's very, very similar. In fact, when I first saw this, it was so similar that I thought I maybe plotted the data into the wrong axes. So I made a plot to compare these two, and you can see it's 10 to the -3. So it's crazy how similar these two are. Now let's have a look at the first few principal components. So what we see here is the new basis vectors. So the 0th component is the first basis vector in our new basis that explains the most variance, and you can see that it's almost only ones. So, or if we normalize it, all ones over times 1 over L. And yeah, that's, if you think about, is exactly like the magnetization, because if you multiply this first basis vector times any value, you get just the constant grid at magnetization and M. And then for the following principal components, you get some structure below to get more fine details into it. But yeah, the first principal component is just ones everywhere, and it describes the magnetization quite well. And then here we can just create a simple animation to show the components changing over the number of the component. Yeah, it's basically just this this plot into a animation, and if we look at it, you can see that for higher numbers of the principal component we get more fine details. And yeah, so in the next video we're going to try to do that with a more general approach using variational autoencoders, and we're going to compare the two results that we got here from principal component analysis and from our analytical solutions. What I'm doing here is from a paper that I'm going to link you in the description. And yeah, see you next time.